showers weekly. There shall be showers of blessings, precious reviving again, over the hills and the valleys, sound of abundance of rain, showers of blessings, showers of blessings we need. Mercy drops round us are falling, but for the showers we plead. There shall be showers of blessing, oh that today they might fall. Now as to God we are confessing, now as on Jesus we call. Showers of blessings, showers of blessings we need. Mercy drops round us are falling, but for the showers we plead.
Prayer. Our Heavenly Father, we thank you for giving us a new day in our lives. We acknowledge you as the creator of everything in this universe and bow before your mighty name. Let this time we are all connected in this webinar session and pray to you for your guidance, knowledge and wisdom. Bless the resource person, all the staff and students who are participating. Let this time be very useful of all of us so that we may gain new knowledge in this particular area of physics. We ask in the name of our Lord and Savior Jesus Christ. Amen.
Respected Secretary, beloved Principal, distinguished guests, enthusiastic participants, and my dear colleagues. Good morning to one and all join in this webinar series. It gives me immense pleasure to welcome you all to the international webinar series on recent explorations in complex systems, dimensions and atomic physics, RECAP'21. I happily welcome our principal, Dr. Usha Godwin, who is also the patron of this webinar series. At this juncture, I gratefully remember the best wishes and cooperation rendered by our Secretary, Reverend Soundra Pandian. Conference is a celebration of knowledge where eminent researchers share their knowledge and experience. Thus today, we are privileged to have Dr. J.S. Raj Vellore Winfred from United States of America for the first session of the webinar. Welcome you, sir. Also, I give a warm welcome to Dr. S. Nirmal Tyagu, Madras Christian College, Chennai, and Dr. Sanjit Das, VIT Chennai, for the second and third day sessions of this webinar series. Now I will introduce Dr. J.S. Raj Vellore Winfred. At present, he is working as a scientific research specialist in Florida State University, USA. He finished his undergraduate course in Bharathidasan University, Coimbatore, and postgraduate course in IIT Chennai. He obtained his PhD from PTB, a National Metrology Institute of Germany, on the title Investigation of Collisional Losses and Decoherence in a 1D Optical Lattice Clock with Strontium-88. Dr. Raj started his career as the head of Physics Tutoring Division, Tutors Worldwide, Chennai, and then worked as a project assistant in Raman Research Institute, Bangalore. He completed 1-year internship and worked as a doctoral student for 4 years in PTB, Germany. Regarding his working experience, he was a research fellow in Nanyang Technical University, Singapore, worked as a private physics tutor, acted as post-doctoral researcher in National High Magnetic Field Laboratory, USA, worked as an adjunct faculty in Florida A&M University, USA, and currently he is working as a scientific research specialist in Florida State University, USA. He has published many papers in reputed journals like IEEE, Transaction on Instrumentation and Measurement, Physical Review Letter, Metrologia, Physical Review B, and so on. Once again, I welcome the eminent resource person Dr. J.S. Raj Vellur Winfred to this session. He will enlighten us with his speech on the topic, a bird's eye view of state-of-the-art techniques to probe atoms and molecules. Now the platform is yours, sir.
The university is located, its name is Tallahassee. So typically, Tallahassee weather is more or less like Chennai weather, especially from April to October. And then the Tallahassee, let's say winter time is somewhere from 5 to like 30 degrees centigrade. So the temperature is more or less similar to what we have in our state, especially during the summertime. It's quite humid here. So what you see in the slide is the university campus. Florida State University, it is ranked 18th among the national public universities here in US. And the university is also home to MagLab, which you see over here. So it's the National High Magnetic Field Laboratory. And this lab has the world's strongest magnet here. That you can see in this picture. So we can generate magnetic fields up to 45 Tesla. And this facility is primarily used to study materials under extreme conditions. By extreme conditions, I mean low temperatures, high magnetic fields, and high pressures. Some of the famous people from FSU, the most notable one, namely the Paul Dirac. He's one of the founding members of quantum mechanics. And Kroto, he is the discovery of fullerenes, also known as buckyballs, carbon nanotubes. And Dr. Mulliken, so he is the development of the, he was responsible for the development of the molecular orbital theory. And last but not least, Schiffer. So he's one of the pioneers of the development of the theory of superconductivity, which is commonly known as the BCS, theory of superconductivity. The S stands for the Schiffer. So that's like a brief introduction about the university here. Regarding the department, so our department here, which is a Department of Chemistry, you see the building over here. So it was established in 1901. And it was also instrumental in developing a core research facility and also the National High Magnetic Field Laboratory. The department houses 3 core facilities, MagLab, for which I'm the director, and then you have an NMR facility and also mass spectrometer and X-ray facilities here. So the main research work done in the department is mostly like analytical, physical, materials, organic and inorganic, and also biochemistry too. Okay, so for this talk, I will give a brief overview of the instruments that we have in the MagLab, and just to be sure that this talk reaches a wide range of audience, I have selected like 2 main core areas of research work that is primarily it's like hot right now, which is magnetic properties of materials and also ultrafast spectroscopy. So I will briefly go through the instrument and the techniques that are used to measure magnetic properties, and also the instrument and the techniques that are used to measure ultrafast processes in various systems. And finally, I would end this talk with some career opportunities as a core research facility manager, also in India too. Okay, so the MagLab instruments over here. So we have a state-of-the-art instruments that are mainly used to study material characterization of like a wide range of systems. So They can be broadly categorized into like physical, where you have a squid, an EPR and an AFM, thermal analysis, you have like a TG and SDT, and optical group, which has a wide range of spectrometers and also other absorption and quantum yield instruments here. So for this talk, I will mainly focus on two instruments and the principles behind them and how they are used to study magnetic properties. First one is a SQUID, which stands for a superconducting quantum interference device, and then a femtosecond, a transient absorption spectrometer. Okay, so SQUID. SQUID, as I mentioned before, it stands for superconducting quantum interference device. So what you see in this picture is a SQUID magnetometer. So magnetometers, they are used to study magnetic properties of materials. We can also study temperature-dependent properties, magnetic properties of materials. And this instrument houses a superconducting magnet that can produce fields up to 7 Tesla. So before going into the workings of the instrument, I will just devote 2 to 3 slides on some basics of superconductivity. Out of the superconducting quantum interference device, the first part is superconducting. So as many of you may be familiar, the difference between like a normal conductor and a superconductor. So here in the graph, you see behavior of a non-superconductor and a superconductor. So we have the temperature versus the resistance graph. And for the normal conductors, like for example, copper and everyday materials that we use, its resistance decreases as we lower the temperature, as you see over here in this graph. But whereas for superconductors, they are a little bit different. So for superconductors, what would happen is that as we decrease the temperature of the material, its resistance decreases, but at a certain temperature, known as a critical temperature, the resistance goes to 0, which means once a current passes. Yes. Good morning.
Good morning, sir.
Good morning. Okay, so once we reach a critical temperature, then the resistance drops to absolute 0, which means that if a current passes through a conductor, then it will run for, in principle, infinite time, because there is absolutely no resistance at all. So in order to just briefly discuss the difference of behavior between like a normal conductor and a superconductor, you can actually look at this diagram over here. So in this diagram, what we see here are different atoms arranged in a solid. So as you may know, in a solid, atoms are arranged in a crystalline lattice structure, and at normal temperatures, by normal temperatures, I mean like higher and room temperatures and so on, there is thermal agitation of the atoms that you see here. So the atoms are vibrating. So the red lines that you see, so these are the electrons that are passing. So as the electron passes, they get scattered due to the vibration of the atoms. And this is the reason why you have resistance at normal temperatures. What happens for superconductors? Well, for superconductors, it also behaves similar to a normal conductor as we decrease the temperature, but at the critical temperature, the resistance suddenly drops. So the reasons why the resistance drops suddenly is because of this diagram that would illustrate the principle here. So we have the same atoms that are arranged, but as you lower the temperature in a superconducting material, the agitation, or let's say the vibration of the atoms, they get very, very small. So as they get very, very small, what would happen is that the interaction between the atoms and the electrons, which is the Coulombic interaction, increases. So imagine an electron that is traveling in this direction as shown over here. So as this electron travels, the first electron travels, it would create an attraction, which is shown here because of the Coulombic interaction. And this Coulombic interaction, it would have a higher positive charge. And this higher positive charge would attract an electron that is coming behind this electron here. So as this electron travels, you have this positive charge, higher positive charge density, and the electron behind it would be attracted towards that. So these two electrons in a superconductor, they form a pair, something called as a Cooper pair. As you may know, that electrons, they are fermion particles. They have spin half, but when they form a Cooper pair in a superconductor, they form together as a one single particle. So we can no more distinguish these two electrons as separate, but we will be treating these two electrons as one single particle, therefore forming a boson. So how do these two electrons interact? So these two electrons, one is like spin half, plus and minus spin half, and they interact each other, and these two pairs and these two electrons can be represented by a single particle, free particle wave function, which is also known as the de Broglie waves. So that forms, or that explains how superconductivity is observed in certain class of materials. Now let's go to the quantum interference part of the squid. So usually what would happen if you have a superconductor, and if you separate the superconductor by a very thin insulator, any Cooper pair can go from one side to another through a phenomenon known as quantum tunneling. The reason why it can happen is because you have very low temperatures, and the normal classical physics that we usually learn in the undergrad and in schools no longer applies there. So here, quantum tunneling is possible, which means that a probability of your superconductor, a Cooper pair passing through an insulator is finite. And this tunneling phenomenon is called Josephson tunneling. Okay, so how is this applied in a squid? So what we see over here is a superconducting ring. So this superconducting ring, you have a superconductor, and it is separated by a very small insulator shown in this, shown as like a white stripe over here. So a very fundamental principle about a superconducting ring is that the magnetic flux that passes through this ring is quantized. So any magnetic flux has to be an integral multiple of this flux quantum that is shown over here. So this flux quantum, it depends on the fundamental constants, for example, your Planck's constant and the charge of the electron here. So this phenomenon that the magnetic flux through a superconducting ring is quantized is taken advantage when measuring magnetic fields for very, very low values. So how does it work? So for example, imagine if you're passing a current through a ring. So from our basic electricity and electronics course, you would know that whenever the current passes through a junction, it splits into two, as shown over here. So a current I passes, and then like half of the current passes through this side, and then another half of the current passes this side, and then finally they get joined in this junction and come out. Okay, so now what would happen if we apply a magnetic flux? So if we apply a magnetic flux due to electromagnetic induction, a screening current emerges in this conducting wire over here. So the direction of the screening current depends on the integral multiple of your flux, which is the phi naught over here. So the direction of the current, and then any change in the current would result in an oscillating voltage that is measured across the two junctions that is shown over here. This phenomenon is what is used in a squid. So a squid can measure very weak magnetic fields, and hence the name a squid magnetometer. Okay, so how does a squid magnetometer look? So this is a cross section of a superconducting magnetometer that you see over here. So this is the area where your sample is usually placed, and here you have the detection coils, and this is your superconducting magnet. So this whole area is actually filled with liquid helium. So superconducting magnets, they function at very low temperatures, at around like, so they begin to superconduct, they go into superconducting mode at around like 4 Kelvin. And then here you have the squid, which would detect your magnetic field of your sample. And this is a magnet here, and this magnet is what is used to apply very high magnetic fields. Okay, so this diagram briefly shows what's happening in a squid. So we apply a magnetic field, a very strong magnetic field. This magnetic field would magnetize a sample. So this sample is basically kept in just a normal drinking straw, because a normal drinking straw is not magnetized when you apply this magnetic field. So the sample is then moved up and down through this coil that you see over here. So this applied magnetic field would result in the magnetization of the sample. And this magnetization of the sample would itself give out its own magnetic field. So as you move the sample through the coil, you would have change in flux through these coils over here. And this change in flux through the coil would result in a current. And this current would go through the circuit that you see over here. And this current is actually inductively coupled to the RF squid. So there is no direct connection between this part and this part over here. It's inductively coupled here. And the detection current, as it is coupled into the squid, and then any change in the voltage fluctuations that you see, which is measured, would result in a graph that is typically shown over here. So here, as you move the straw, or as you move the sample position, your voltage that is measured across would show such a typical curve that you see over here. And the area under this curve is calculated, and that area is actually proportional to the magnetic moment of the sample. Okay, so magnetism in materials. Many of you may be familiar with this couple of equations that are shown over here. So if you apply any external magnetic field onto a sample, the sample gets magnetized, and then it would emit its own magnetic field. So the flux density is given by this equation over here, where H is your applied magnetic field, M is a magnetization of the sample. And you also have another variable over here. So magnetic moment, which is product of the volume of the sample and the magnetization. So the characterization, the magnetic properties characterization of compounds can be broadly classified into like two ways. So one, you can measure magnetic susceptibility, which is the ratio of the magnetization to the applied magnetic field, or the magnetic permeability, which is the ratio of the flux to the applied magnetic field. So every material in nature exhibits some kind of magnetic behavior. But when you want to characterize a magnetic property of a material, you would broadly characterize it by using two types of measurements. So number one is magnetization as a function of applied magnetic field, or the magnetization as a function of temperature. So these two measurements are done in a squid magnetometer by first fixing the temperature of the sample and applying the magnetic field to get M as a dependent of H, and fixing the magnetic field, and then excuse me, measuring the temperature, varying the temperature, and studying your magnetization of the sample. Okay, so different class of magnetic materials that you see over here. So here you can see different types of magnetism that are commonly observed in nature, starting with diamagnetism, where the diamagnetism, your atoms have no magnetic moment, so which means that when there's no external field, there's no magnetic moment there, and this phenomenon is actually observed when you actually apply external field. So when you apply external field, the electrons, they're precise, and this produces a magnetization over here. This magnetization is actually opposite to the direction of the applied field, and typically the susceptibility is independent of the temperature. The materials that are more commonly of interest from the application point of view are paramagnetism, ferro, antiferro, and ferrimagnetism. So paramagnetism, what happens is that you have atoms which are shown in this diagram over here. They are arranged in lattice, and they are usually they are randomly oriented because of thermal agitation. But when you apply a magnetic field, an external magnetic field, it would make these magnetic moments align. So as you increase the field, the alignment increases. So therefore, the sample gets more and more magnetized, is what you see over here. So when you apply an external magnetic field, shown in here in the x-axis, the magnetization of the sample would increase too. And the susceptibility values for paramagnetism is usually small, and they're positive. But there are also different types of paramagnetism exist. Ferromagnetism is what we normally see on a day-to-day life. So for example, your daily magnets that you come across, they're all ferromagnets. So what distinguishes ferromagnets from other two that I just mentioned is that the atoms here, the magnetic moments are perfectly aligned, and they are parallel to each other. So this means that any small application of your external field would result in a large magnetization of the sample. So that's the reason why you see a very steep curve over here. And afterwards, of course, the magnetization saturates because all the atoms are perfectly aligned. And the susceptibility values for ferromagnets are very large. There are also like other one, which is antiferromagnetism. So in case of an antiferromagnetism, it's very similar to ferromagnets, but their magnetic moments, they're not all aligned parallel to each other because of the interactions between the neighboring atoms. So this would result in anti-parallel alignment of magnetic moments. And sometimes they also appear to behave as paramagnets. And the reason why you would say that is because your M over H behavior for paramagnetism and also for antiferromagnetic materials, they are very similar. Last is the ferrimagnetism. So the ferrimagnetism is similar to the ferromagnets. The only difference being is that their magnetic moments, some of them are parallelly aligned, but some of them are antiparallels. So they have a mixed parallel and antiparallel alignment. And their behavior is also similar, as you see over here. But their susceptibility values are much, much smaller than ferromagnetism. Okay, so after giving a brief introduction to the different types of magnetism materials, let's go ahead and see how they are characterized. So this graph that you see over here is for a compound, is a superconducting compound. So this is measured at temperature of 100 K. What you see over here is a typical behavior of a paramagnetic material. So paramagnetic material behavior is the most simplest of all magnetic behaviors. The line or the behavior is linear. So on the x-axis, you would see the applied magnetic field, and then on the y-axis is the magnetization of the sample. So as you can see, as you increase the magnetic field, applied magnetic field, the magnetization also increases. So which means that when initially, when at zero external magnetic field, the atoms are all aligned differently or randomly aligned. But as you apply external magnetic field, the magnetization goes up. And this magnetization is reversible, which means that if you remove your applied field, then the atoms, once again, their moments, they align randomly. And the slope of this line gives a magnetic susceptibility. So here, what you see is a typical behavior of paramagnetism that can have different types of origins. So in order to determine the origin or what type of paramagnetism it is, you need to actually measure susceptibility versus temperature. So this is a typical graph that you see for the compound that I showed in the earlier slide. So what we've done here is that we have actually fixed the magnetic field and we vary the temperature of the sample. So as we vary the temperature of the sample, you would see that the susceptibility decreases. So this type of behavior, this 1/T behavior, is called Curie type magnetism. Okay, and the reason why you have such a behavior is because the presence of atoms with unpaired electrons. So as we increase the temperature, the atoms, they vibrate more and more, and this would result in a random orientation of your dipole moment, and that results in the decrease of the susceptibility. So what we can infer from this graph, so we can actually find out what the effective magnetic moment of your sample is from this equation that is shown over here. So this behavior, this 1/T behavior, is given by this equation here, where C is a Curie constant. So once we get this information from the squid magnetometer, we can find out what the value of C is for the particular material. And then by knowing the universal constant, which is 1/the Boltzmann constant, and the number of atoms in the sample, we can measure the effective magnetic moment. So that is how you would normally measure magnetic properties of Curie type paramagnetic materials. There's also another type of material which is called Curie-wise magnetism. So this magnetism is actually results in the interaction between different magnetic moments of the atoms, of the neighboring atoms. And this interaction would lead to alignment of the magnetic moments either in the same direction or in the opposite directions. So that usually depends on the temperature. So what you see over here, once again, is like a typical graphs that you obtain for Curie-wise paramagnetic materials. So they have a particular temperature dependent. This temperature dependent is shown by this expression over here, where theta is the Curie-wise temperature. So for a theta value greater than 0, the interaction help moments align in the same direction. So which means you end up having net ferromagnetic interaction that you see over here. For theta less than 0, for Curie-wise temperature less than 0, the interaction would help the moment to align in the opposite directions, which would end up having an antiferromagnetic interaction. And the ferromagnetic transition temperature, it's called the Curie temperature, and the antiferromagnetic transition temperature is called the Néel temperature. So till now, we have seen how a squid can be used to measure magnetic properties of materials and how we determine different types of materials, whether they are paramagnetic or ferro or antiferro, by varying the temperature of the sample or by varying the magnetic field of the sample, and by also studying the interactions. So course, one common question most of them would ask, okay, why do you want to do this? Magnetism studies is one of the fundamental studies that has a very broad application, as seen in the slide over here. So when we study magnetism and magnetic properties of materials, so not only from the physics point of view, where we can actually study like different types of phase changes in materials, and it actually opens up a lot of rich physics to be discovered, but also from a practical point of view, study of magnetic properties of materials would enable us to actually manufacture more powerful permanent magnets. So this, of course, would lead to a lot of other applications, for example, your information storage, like a hard drive and so on, and any types of magnetostriction applications, and of course, your signal transfer, electric circuits. Miniaturization is another hot topic, which would involve a lot of studies of magnetic properties of materials, which again would be applied to automotive electronics. And needless to say, medical fields where the MRI, more and more powerful and compact MRIs are needed to study or to diagnose different conditions, different health conditions. And in the end, it also helps us to generate much more larger magnetic fields. Okay, so moving from magnetism, magnetic properties of materials, now I will give a presentation on a totally different but also equally important technique. It's called ultrafast spectroscopy. So ultrafast, why do we need to like study an ultrafast phenomenon? So this table over here shows us the different processes occurring in nature and the typical time scales. Okay, so right from the start of the evolution of the species to a typical lifespan that we have, typical the animal movement, and then once you go to like biomedical reactions or biophysical reactions, you see like the protein synthesis, like how long does it take, for example, and then any kind of signal action potential against, for example, like a neuron. And as we go lower and lower, you would see that the processes that take place at a very, very short time scale. So in order to study these processes, especially in the biophysical processes, we need a system that has a time scale much less than the process itself. So a best way to explain that is by looking at this picture over here. So here you actually see a hummingbird taken with the picture with an exposure time of about like 1/60th of a second. So at 1/60th of a second, you can see the bird, but the bird's wing flapping is so fast, it's much faster than 1/60th of a second, and therefore it occurs very blurred. Now, what would happen if you actually decrease your exposure, which means if you start shooting it much faster and faster? So if you start taking the images much faster and faster, here you actually see the bird at every single step. So here your wings is no more blurred. You can actually see the phenomenon that's happening. And this is the reason why you need to have ultra fast studies in order to probe any kind of biophysical processes that occurs in, let's say, in the picosecond and in femtosecond time scale. So the ultrafast studies is not only limited to biophysical processes, it's also applied in physics. For example, in physics, we can study electron-photon coupling, coherent photon dynamics, and also photo-induced phase transitions. Okay, so the main workhorse for an ultrafast spectroscopy is an ultrafast laser. So the time resolution that I described earlier in the slide, it comes from very short flashes of laser pulses. So how do we generate such a short flashes of laser pulses? So in order to understand how do we generate laser pulse, let's first have a look at a normal laser that we have, like for example, a laser pointer. A laser pointer is a continuous wave laser. So how does a laser produce the light? So here is like a brief example that shows. So in a laser, you typically have two mirrors and a gain medium. Okay, so what we do is that we energize this gain medium, and when we energize this gain medium, all the electrons that are in the ground state, they go to the excited state, and then when they go to the excited state, they come back to the ground state by spontaneous emission and also by stimulated emission. So when the stimulated emission rate increases, then more and more light comes and hits these two mirrors, and once the lasing action begins, you would get the laser output here. So that is like shown with this very simple example. So in this example, you see like a container in which the water is flown, and there is a hole over here which continuously drains the water from there. So this is like a very easy way of understanding what's happening in a continuous wave laser. Now, what would happen like in a Q-switch laser? So a Q-switch laser is used to produce ultra short laser pulses. So in a Q-switch laser, you still have the two mirrors and a gain medium, but what we do is that we have an attenuator. So this attenuator actually blocks the light from hitting the two mirrors. But at the same time, what we do is that we energize the gain medium. So as we energize the gain medium, all the electrons in the ground state is going to the excited state. You see in the previous one, not all go to the excited state, only a few go into the excited state. But here, since we have an attenuator and we give enough time for the gain medium to transfer all the electrons from the ground to the excited state. This is similar to having the same system, but rather plugging in the hole. So once you plug in the hole, the container fills up completely. And when you move away this attenuator, all the electrons from the excited state, they all come to the ground state at the same time. So when they come at the same time, there's a sudden burst of laser pulse, which is of very high power. It's similar to what you see over here. So here, once you remove the cork, all the water just gushes out at a very high force. So that is how you would produce pulsed lasers. So here you can actually see in this graph over here, the output power versus time. So for a continuous wave laser, the peak and the average power is more or less the same and it's low. But whereas for a pulse laser, you have very brief intervals of high power pulses coming out. Okay, so this is your peak output power, and this is like your average output power here. So typically when you try to characterize a pulse laser, so you would characterize by using these parameters over here. So here you see a typical output of a pulse laser. So you have a pulse energy on the y-axis and the time on the x-axis. So here you have different train of pulses. So every single pulse is characterized by this pulse width, which is the time for which the energy of the light goes up to the maximum, then comes down, and also the repetition rate. So which is basically like how many pulses of a laser you have per second. Okay. So as I mentioned before, the pulse lasers, they are of very high power, and they can easily damage any optics that is there in the path. So in order to get a really high pulse lasers, high power pulse lasers, we actually do like different steps are required here. So these steps are shown over here. So this is like the basic components of an ultrafast laser. So an ultrafast laser consists of an oscillator, a stretcher, a regenerator amplifier, and a compressor. So what does an oscillator do? An oscillator is a Q-switch laser that I mentioned in the previous slide. So they emit pulse lasers, but their energy is very low. So here you see it's about like 3 nanojoules. That's very low power. and the pulse width is about like 60 femtoseconds over here. Now, if you want to increase this energy, what we need to do is that we need to stretch the pulse. By stretching the pulse, what we're actually doing is that we are stretching it by time. So we are taking a very narrow pulse and we are stretching it really broad. So that's why this name is called stretcher. So in the stretcher, the pulse width is stretched from 60 femtoseconds to 200 picoseconds. Okay, and when you do that, the pulse energy also goes down because of the stretching. And then what we do is that we take this pulse that is coming out from the stretcher and we use an amplifier. This amplifier actually amplifies the power. So as you can see, this amplifier amplifies the power from 2 nanojoules to 3 millijoules, but we still have 200 picoseconds. Now, how do we reduce the pulse width? We reduce the pulse width by taking the pulse out of the regenerator amplifier and sending it to a compressor. The compressor would compress the pulse from, let's say, 200 picoseconds to about like 100 femtoseconds. And as you can see, the power is very high. So we went from 3 nanojoules to up to 2 millijoules. That is orders of magnitude more than what we started. We cannot have 2 millijoules right out because this would damage your optics. And that's the reason why you end up having so many steps in order to produce an ultra fast laser pulse. So this is a setup that I have in my lab. So we have the laser that is shown here in this figure. So this is a coherent ultra-fast laser. So this laser is capable of producing pulse lasers of 100 femtosecond pulse width at 800 nanometer peak wavelength. And it has a repetition rate of about like 1 kilohertz, which means that it can produce 1,000 pulses at within a second, in 1 second. And this output of this laser goes into another system called an OPA. OPA stands for optical parametric amplifier. So I'll explain it in the next coming slides what it basically does. So basically what it does is that it takes a light that has a wavelength of 800 nanometers and then produces light of different wavelength. So it can, for the OPA, for the typical OPAs, we can actually go from somewhere from 200, like 300 nanometers to up to like 2.5 microns. And in this picture over here, you see a transient absorption spectrometer. So this transient absorption spectrometer is capable of studying phenomenon that has a lifetime from about like 100 femtoseconds to up to like 8 nanoseconds range. So this setup shows the laser part inside. Like we saw on the previous slide, we have an oscillator over here. So the light from the oscillator comes out, and this box has a stretcher and a compressor. So the pulse is stretched, and after the pulse is stretched, it goes into the regenerator amplifier, which is shown in this part over here. And this regenerator amplifier needs a pump laser. The pump laser is actually coming from here, and after the pulse power is increased, it once again is sent into this box over here where it is compressed, and then the laser output comes out from here. Okay, so the small animation shows what's actually going on. So you have the laser pulse coming from here, and then it goes to a pulse stretcher, and then finally it comes into the regenerator amplifier region that is shown over here. So this is a pump beam. So as you can see here, as the beam goes through several reflections, the pump power increases. And afterwards, after a certain period of time, the amplified light is ejected from this cavity, and then it goes into the pulse compressor, and then finally you get the output there. Okay, so how do we generate light of different wavelengths? So we generate light of different wavelengths by a nonlinear phenomenon called harmonic generation and optical parametric generation. So these are different ways to access different wavelengths of light produced other than the laser that is used to produce ultra-fast pulses. So here, just like briefly describe, showing a couple of phenomena that you see over here is that number one is a collinear second harmonic generation. So basically what happens is that it takes two photons of the same energy, and then the output photon is twice the energy or twice the frequency of the input photon. In some frequency generation, you take two photons of different frequencies, and the output is the sum of the two input photons. The frequency is the sum of the frequencies of the input photons there. Optical parametric generation, here you have one photon that comes over here. It's called a pump photon, and this pump photon is then split into two photons over here. So it's called as a signal photon and then the idler photon. So typically the signal photon has a much higher power than the idler photon. So that's how you generate a different wavelength. And finally, optical parametric amplification, where the phenomenon is same, but except in this case, you have a seed signal which would generate a much stronger a signal and the idler photons. Okay, so here in this diagram, you actually see what's there inside an OPA. You have the light that comes from your ultra-fast laser, and it goes through different paths, beam paths, and we have a crystal, which is the calcium fluoride crystal, that's used to generate white light. So that's what you see in this picture over here. So this white light generation is used to produce different wavelengths over here. So it goes through like different optics and different crystals, and finally the output that comes out over here, you can have access wavelengths anywhere from UV to up to like IR, near IR. Okay, so the pump probe spectroscopy is one of the fundamental techniques of ultra-fast spectroscopy. So what happens in this pump probe spectroscopy is that we have a light that would excite your atom or molecule, and then you have a probe light that actually observes the decay of the excited state. So here in this diagram that you see on the right side, it's an energy level diagram. So you have the atoms, they're usually in the ground state, and then when the pump excitation happens, the atoms in the ground state, they are transferred to an excited state, shown over here as singlet 1. And from this state, there are several different mechanisms are possible. So they can decay to a triplet state that is shown over here, and then finally, once again, decay back to phosphorescence. Of course, you also have fluorescence too, where it goes from the excited state to back to the ground state. But in order to study the lifetime of these excited states, for example, the singlet and the triplet states, we apply the probe pulse. So when you apply the probe pulse, if there's a decay from these states, the probe absorption decreases. So that is how you would study the lifetime of these excited states. So this is a typical setup of an ultra-fast pump probe spectroscopy experiment. So we have the laser that would give us the ultra-fast pulses, and this light is split into two by this beam splitter over here. So part of this light goes into the optical parametric amplifier, where we can generate different pump excitation light, and then it goes through like an optical chopper, it goes through a couple of optics, and then it goes to the sample, it excites the sample. Another part of light is actually goes through something called a variable delay. So variable delay is actually a moving mirror. Keep in mind that we are actually probing phenomena that are from in the femtosecond to nanosecond ranges. So we don't really have electronics that are fast enough to actually delay your pulsing between the pump and the probe. And that's the reason why we actually use a mirror to manually move the light so that the light from of the probe comes after the pump pulse. So the light from the probe comes over here. It goes to a crystal. This crystal generates a white light, and it goes and hits a sample after the pump. So your decay of these excited states is measured by the change in the optical density. So the optical density is calculated by this expression that you see over here, where the numerator is actually the probe of the intensity measured before the pump pulse, and the denominator is the probe intensity measured after the pump pulse. So here is a typical example of a wavelength-dependent pump probe spectroscopy result. So this result is for a typical Ruby P sample. So here you actually see the on the y-axis you have the optical density, and then on the x-axis you have the wavelength, and these different graphs are for different time intervals. So what's happening here? First, you excite your sample by using the pump laser. So the atoms or the molecules, they actually go from the ground state to an excited state. And then once they go to the excited state, they decay either to the triplet state, and then from the triplet state, they come back to the phosphorescence, they come back to the ground state to the phosphorescence. But if you want to like measure the lifetime of these excited states, you would apply the probe pulse. So if there are a lot of atoms, a lot of molecules in the excited state, then a lot of absorption will be there. If there are less number of atoms or molecules in the excited state, then the absorption will be less. And that's why you see this change in the absorption, because as the time increases, the absorption goes down. So you have like typical, so this is the first part that you see, and the first peak that you see over here is your absorption. And then there's something called ground state bleach. Ground state bleach occurs because you have the atoms that are in the ground state, which when you excite it to the excited state, and then when you apply a pump pulse, the probe pulse, you wouldn't be able to see like a lot of atoms over here. So therefore, you have like much more light going through. So therefore, the OD, optical density, is negative over here. And finally, the luminescence is what you see because of the phosphorescence method. So here in this diagram, you see a typical transient decay that you observe in materials. So you have the pump light that would excite your sample, and then we are delaying the probe here. As we delay the probe, there'll be less and less molecules in the excited state, and therefore the absorption of the molecules in this excited states go down. And you would typically, for simpler compounds, you would see a mono-exponential decay. But if you have decay states of like more than one, then you would also encounter bi-exponential and tri-exponential decays too. So that kind of gives like the brief overview of the ultrafast spectroscopy and how it is, this technique is used to study ultrafast phenomenon in different compounds. Okay, so finally, so as I mentioned before, I'm the director of a laboratory. So there's something. So this is probably would be of interest for the students in the department or the seminar, is being a manager or a director of a core facility. So this is another career option for students if they want to like stick to the research, but also would want to like keep a foot on different techniques and over time become an expert in like different techniques over here. So what's basically a core facility is that a core facility usually has a centralized place where for researchers can come and use instruments there. So these facilities are typically operated by fee-for-service labs, And these facilities can be accessed by different research groups in academia and industry. So most of the time, users accessing such research labs, they have to undergo training before using the instruments. And research faculty and staff, such as me, we are responsible for like training the instrument, for training the instrument maintenance, experiment design, and specialized services. So these core facilities are they're also in India too. So I have just like named a couple of them over here. So for example, you have central research facilities at different IITs. There's also like one, the analytical instrument facility at IIT Madras, and also one like in Wales, Chennai, and also like instrumentation center, and also Madurai Kamaraj University. So if you have students who are interested in like going into this kind of career path, then this would also be like an attractive option for them. That ends my talk, and I thank you all for your attention. And if there are any questions, I'm ready to take them.
Participants, dear participants, you may unmute and raise your questions to Dr. Raj. Participants, do you have any queries?
So, Dr. Raj, this is Nirmal here. I would like to ask a question on behalf of the students. So, the students in India who would like to pursue higher studies in the US, for example, if they need to crack the exams like GRE, what kind of preparation they should involve in, what kind of methodologies, what are the system of studies, when should they start preparing? So that kind of an overview, if you give brief overview, it will help them enormously, I think. Thank you.
Yeah. So in order to pursue higher studies here in US, one has to clear an exam called a GRE, which stands for Graduate Record Examination. So there are actually two types of GREs. So we have like a general GRE and then a specialized GRE. So these two examinations, specialized GRE is any subject that you want to like apply for. So for example, if you want to apply for a physics graduate school, then you would want to apply for like you should clear an exam for physics. What I would recommend is that if you set your aims to pursue higher studies here in US, your fundamentals should be really strong. There are several books that are available, especially in this day and age. It's very easy for you to search. But one main point that would set your application apart from other application is that doing a project. I would highly recommend that students who want to pursue higher studies here in US do some kind of a research work either in the undergrad or in the postgraduate. So you can contact faculties at different institutions. So like a summer school. So if you can join like a summer school and then just take a project. So this would definitely help you set apart from other students because it shows that you have taken initiative and you're really interested in pursuing research.
Thank you, Dr. Raj. In addition, also another note I wanted to make is that students who do physics irrespective of theoretical or experimental work have to have a minimum exposure to the computation, for example, some programming language. So you are an expert in the experimental area. So do you also concur with this? And if so, would you advise students of physics to learn any particular language which will help them or some other softwares which will help them?
Oh yes, I mean, being an experimentalist, I also do programming a lot. It's just a part and parcel of being an experimentalist. So, so for me, I mainly use programming, or I do programming to for data acquisition and also for data analysis too. So learning a programming language is very important for students. So nowadays, Python is a language that is quite popular among physicists. So that is it's a language that has applications across different branches. It's like a Swiss Army knife for like a lot of applications. So if you learn Python, you can do anything from data analysis to data acquisition, and also like programming other instruments and so on. So yes, so it's definitely an essential skill for an experimentalist to learn a programming language.
Okay, thank you, Dr. Raj. Now it's almost 12:45 or 48 in the US,
Yeah,
and
yeah, totally. Yeah.
thanks for yours.
Dr. Lindsay Mary, Assistant Professor of Physics, Saratoga College, will deliver now the vote of thanks.
It's my great privilege and honor to propose the vote of thanks on this webinar. I take this opportunity to place on record a hearty thanks to the Secretary, Reverend D. Soundrapandian, and the Principal, Dr. Usha Godwin, for the guidance they have extended to us. I must mention my deep sense of appreciation for Dr. J.S. Raj Veloor Winfred, Scientific Research Specialist, Florida State University, USA, for giving an excellent coverage to superconducting quantum interference devices. Sir, now we are all aware of Cooper pass, speed magnetometer, magnetism in materials, ultrafast spectroscopy, etc. You have explained in a simple, understandable way with necessary graphs, pictures, and examples. Once again, I mention my deep sense of appreciation and gratitude to the speaker, Dr. J.S. Raj Veloor Winfred. I also
Thank you very much.
express my gratitude to Mrs. D. Jagadi Jasmine, convener and head of the Department of Physics, for her encouragement in organizing the webinar. I may like to express my sincere thanks to Dr. T. Vardhini, Organizing Secretary and Associate Professor of Physics, for her tireless effort. We have been backed and fortunate enough to be backed by a team of very motivated and dedicated colleagues of Department of Physics, Saratoga College. Last but not the least, I thank all the participants of the webinar. Thank you, one and all. Posted up. Dear participants, the feedback link is posted in the chat box. Kindly submit it. The session is over. We'll meet again on Monday, the 23rd August at 10 a.m. for the next session. If you have submitted the feedback form, you may leave the meeting. Thank you.